Okay, Bismillahirrahmanirrahim. Assalamualaikum and a very good afternoon. So today we're going to continue with the next subtopic of the first chapter. Okay, so next we are going to look at discrete time signal and systems. Okay, in the previous lecture we have learned on continuous time signal. So if you still remember, continuous time signal, it could be in continuous time in T domain, or you can also have the digital signal still in T domain. Okay, but now we are going to look at discrete time signal, which will be in N domain. Okay, let's look at the main comparison between a continuous time signal with discrete time signal. Okay, on top here is continuous. This is the continuous time signal, in which the signal have continuous amplitude at all instants of time. So the domain is T. And for discrete time signal at the bottom, you can see that each signal being having a specific amplitude at specific instant of time. Okay, so this is in N domain. The figure below shows how the discrete time signal is generated. So if you remember, in the first topic we have discussed on the system, the continuous time system, in which you have input signal as xt and then being transmitted into a system. This is the system, and then the output is generated. Okay, but in discrete time signal, the input signal is in T domain, continuous time signal or analog signal. The signal being transmitted into a system or a processor, commonly ADC, analog to digital converter, in which it will convert the input signal in time domain to discrete time signal. So the output now already in N domain. Okay, why basically we need discrete signal or digital signal? Okay, so in earlier version or earlier system, the input is in time, in continuous time signal, being transmitted into a system that process the continuous time signal and then being transmitted to the receiver, and the output YT is received. Okay, but in new era, most signal has been digitized. Why? So that the system and the transmission medium, so transmission medium is somewhere here, okay, usually use digital transmission system, okay, in which only digital signal can be transmitted over the channel. Okay, so so why they design a digital transmission system? Because they want to reduce the noise or distortion due to the analog or continuous signal. Okay, so digital signal is more can minimize the effect of noise. Okay, so this is how the analog signal being converted into digital. So firstly, you can see that the gray color graph is basically the input signal in T continuous time, and then the signal will be quantized. Okay, quantized meaning that it being divided into multiple levels. Okay, the more the level numbers, the better the signal, because it can be resembles closely to the original shape of the input signal. Okay, then the signal will be sampled and coded. Okay, during the sampling, the signal will already get the shape of this digital signal, and then it will be code or coding, okay, to get the digital sequence 0 1 0 1 0 and so on. Okay, so then you get the finally the discrete signal being generated. Okay, discrete time signal can be represented into types. The first one is numerical method, in which you can see the signal representation in sequence. So but the values shown is not the bit, okay, it's not the location, but this values shows the amplitude at specific location. Right, so if there's arrow, the arrow basically representing the n equal to 0 position. But if there's no arrow shown, so you can assume that the first one is the 0 position. Okay, so what is 0 position? Meaning that, so this is your axis, so this is 0. So in this case, 0, the arrow pointed at 1. So the 0 is pointed at 1, meaning that at n equal to 0, so this is your n. So at n equal to 0, the amplitude is 1. So the amplitude is 1 at 0. Okay, so meaning that, and then 2 is basically is minus 1. At minus 1, the amplitude is 2. And then next one, at 1, the amplitude is 3. Okay, and so on. And the second type of representation is by using graphical method, okay, as the graph I've shown here. Okay, so basically this is the sequence, the bit sequence 0, 1, 2 and so on, and these are the amplitude of the impulse. Okay, each of these is called impulse. If you still remember in the first topic, signal, different types of signal, that's impulse function del t, in which you can see something like this. Okay, this is del t, but in this case it is, each of this is del n, because it's already in discrete. Okay, in discrete n. So this is another graphical representation of discrete time signal. Okay, on top is basically representing the amplitude of each bit. Okay, discrete time signal can be represented in two types. The first one, impulse signal. Okay, if you still remember in discrete time, we have del t, in which it is one impulse at position t equal to 0. Okay, so this one is basically, if you compare with basic shifting equation, del t minus t naught, in which this one is equal to del t minus 0. Okay, what happens if you have the impulse at different position? Just a recap. Okay, this one t, and you have your impulse at 2, and you have the amplitude is 2. It will be 2 del t minus your position. It is at positive 2. So this is your equation, 2 del t minus 2. Okay, same goes to impulse in discrete signal in n domain. So in this case, your n here is del, the amplitude is 1. So it is your n plus minus 0, because it is at 0 position. Okay, so if you have different location of the impulse signal, for example, you have the signal at -1. Okay, the amplitude is 2, for example. So this is an discrete signal. So the equation will be the amplitude del is n domain. So minus your n naught in this case is -1. So overall it is equal to 2 del n plus 1. Okay. Next, the second one is in terms of step signal. Again, let's recap from continuous time unit step function. So if you have ut, how the signal looks like, it is the amplitude is 1 from 0 onward. Okay, in t. Okay, but less than 0, it is 0. This is unit step in continuous time. Okay, but in discrete, you have bit sequence. Okay, you have bit sequence at specific time from 0 up to infinity. Okay, so same concept as the shifting. So we're going to look at how the unit step signal in n domain experience the shifting property. Okay, next, how are you going to write down the equation for this particular signal? So you need to consider the amplitude and also the location. Okay, so remember basic equation del, so the amplitude, and then del in this end minus your n naught. Okay, so whether your n naught is positive or negative depending on the location. Okay, so start from left hand side. So the first one you have here, okay, a minus 3 is the amplitude, and then del n plus 3. Why you get plus 3 here? Because it is at -3 position. So del whatever the amplitude is and minus, so the n naught is -3. So that's why you get plus 3. Okay, you don't have to consider the position where there's no amplitude. So moving to the next one that have amplitude. So next one is at n equal to 1, +1. So you have the amplitude of a1. So this is the a1, the amplitude del n, and minus +1. So that's why you get n minus 1. Okay, next, here a2 at n equal to 2. So the amplitude is a2 del n minus +2. Okay, the rest are zeros until n equal to 7. So amplitude of n equal to 7 and minus +7, you get n minus 7. And please take note that in n domain you use bracket. Please square bracket. Do not use this curved bracket because this is for continuity. Okay, when there are more than one signals in a system, there could be operations involved in between those signals. Okay, maybe the signal may be added, subtracted, divided, or multiplied. Okay, so let's try to write down the equation for x1 and x2n. So x1n equal to the amplitude, so 1 del n minus 0, and then plus the second one here, 2 del n minus, the position is +1. Okay, plus the amplitude is 1 del n minus, the position is +2. Okay, so then you can simplify the equation. It is equal to del n plus 2 del n minus 1 plus del n minus 2. Okay, how about the x2n? So x2n equal to, the amplitude is 1 del n minus 0 plus 2 del n minus positive 1, okay, plus next one 1 del n minus positive 3. So simplify the equation. Del n plus 2 del n minus 1 plus del n minus 3. Okay, let's look at example of signal operations between two signals S1n and S2n. Okay, so you need to consider when you add or subtract or multiply a signal, please consider the operation at the same position. Okay, if for example you add two signals at 0, so make sure you consider at n equal to 0 and also n equal to 0. You cannot add different amplitude at different position. So let's look at the addition. Okay, when you add x1 plus x2, so x1 plus x2, okay, this is x1 and then you need to plus x2. Okay, first start with 0. Okay, make sure it is also at 0. Okay, so the amplitude 1 plus 1, so it is 2 at 0, and then at 1 and at 1, the amplitude is 2 plus 2 is 4, at 2 it's 1 plus 0, so it's 1, at 3 it's 3 here, it's nothing, so it's 0 plus 1, so it's 1. Okay, same goes to multiplication and division and also subtraction. So you need to consider the same position for each operation. Okay, this is multiplication and also division. So please alert which one divided by which one. Okay, so to make sure that you divide or multiply the correct signal. Let's look at the next operation of discrete time signal. So if in continuous time you have yt equal to x negative t. When you have negative, meaning that the signal being inverse in t, okay, not the amplitude, okay, in the bracket. So it's time-based or n-based operation. So you have negative here inside the bracket, so meaning that the signal being inverse in n. Okay, let's look at the first example. When you have xn, so what happens when you have x minus n? Okay, the signal, this is yn equal to x minus n. Okay, meaning that from the original signal, the n being inverse. So 3 becomes minus 3, 2 becomes minus 2, and then and so on. And here negative 1 become positive 1. Okay, so then you need to rearrange the axis. This is the output signal. Let's look at another example. When you have xn, what happens when you have x minus n? Okay, when you have x minus n at positive, here is 1, 2, and 3. Supposedly it is at positive 3, now it becomes at negative 3. Okay, and so on. Next, delay operation, or in continuous time you call it as shifting properties. Okay, in time domain, in continuous time you have yt equal to x t minus t naught. This is the basic equation. But in discrete time signal, you have yn in n domain, square bracket, and then you have x n minus n d or n naught, okay, whatever notation you're going to use, right? So let's look at example. Okay, when you have x n minus 2, okay, don't forget to compare with general equation. So general equation x n minus n naught or nd. Okay, so in this case you have your x n minus positive 2. So meaning that the signal, the original signal, this one being shifted to the right by 2. Okay, so 0 plus 2, you got 2, 1 plus 2, and 2 plus 2 becomes 4. Okay, let's look at another example. So again, compare with general equation x n minus 2. Okay, this one will become n plus 2. So meaning that the original signal being shifted to the left. Okay, negative mean to the left by 2. Okay, now everything moving to the left. Okay, this one moving to the left by 2. So 0 become negative 2. Okay, 2 becomes 0, negative 1. 1 becomes negative 1. Okay, another example. When you have xn and the signal being shifted whether to the left or to the right. So again, compare with general equation x n minus positive 3. So the signal being shifted to the right by 3. Okay, so everything moving to the right by 3. Okay, next is scaling, discrete time scaling. So again, to recap, in time, continuous time, when you have the x inside the bracket at, so the a representing the scaling operation. So you need to compare this one with 1, whether it's larger than 1 or less than 1. If it is larger than 1, the signal will be compressed in t. Okay, if a less than 1, the signal will be expanded in t. So same goes to n. If a is larger than 1, so the signal will be compressed in n. If in this case is 0.5 n, so if it is less than 1, so the signal will be compressed or divided by the scaling factor. Okay, let's look at example of scaling, discrete time signal set scaling. So if you have an equation yn equal to x to n, so let's look at the a. So obviously a here is 2, is larger than 1, so the n will be compressed by the scaling factor, in this case 2. Okay, this is the input signal, the given signal, so you need to scale or compress the n by 2. So 0 divided by 2 is 0, 1 divided by 2 is 1 over 2 or 0.5, 2 divided by 2 is 1, 3 divided by 2 is 1.5. Okay, same goes to the left hand side. So now in discrete time signal, you don't have to consider the one width point. Okay, so you just need to consider the whole number of n. So you don't need to consider the 0.5, and you don't have to consider 1.5. You just need to consider n whole number. So in this case, only 0 and 1, and also minus 1. Okay, so then copy the amplitude. So at 0 it is 1, and then at 1 the amplitude is this one. Okay, and then at negative 1 the amplitude is this. Okay, you don't have to consider the end width point. Okay, so you don't have to consider this one and also this one. Okay, let's look at another example. When you have x equal to n divided by 2, so in this case the end the scaling factor is 0.5, which is less than 1. So we know that the n will be expanded by the scaling factor. In this case, 0.5 equal to 1 over 2. So the signal will be expanded by the scaling factor, or the denominator 2. So let's look at this example. So this 1, 2, minus 1, minus 2. So this one is 1, 2, negative 1, negative 2. Okay, so the signal will be expanded in n by 2. So each of these will be multiplied by 2. Okay, so 1 times 2 is 2. So at this position is 0. And then 1 times 2, now it becomes 2. 2 times 2 is 4. 3 times 2 is 6. Okay, negative 1 times 2 is negative 2, negative 4, and negative 6. So now just copy the one. Okay, so all numbers, all n here are whole number, so you can just copy the amplitude. Okay, so this is 1, and then here a bit shorter, and here a bit shorter too. And how about at this point 2, you have smaller one, and you have smaller one too. Okay, so then rearrange its position. Okay, so when you do it in sequence, you have amplitude at 0, 2, 4, and 6. Okay, you have at 0, 2, and then 4, and then 6. 6, this one equal to, the amplitude is 0. Okay, but at 1 you have 0 amplitude. Okay, so the n sequence will always start from 0, 1, 2, 3, and so on. Okay, but the one that has amplitude only at the values here. Okay, next, what will happen if you have multiple operations in one equation? So remember method 3. So you need to use method 3 when you have more than one operation involved. Okay, so remember this one, you can define it as tau equal to 3n minus 4, and then your n equal to tau plus 4 divided by 3. So you need to calculate the n new based on tau. Okay, for example, you have this signal. So let's calculate what is your n. Okay, so here n equal to tau plus 4 divided by 3. So when tau equal to minus 3, so your n equal to negative 1 over 3. 1 over 3. When tau equal to minus 2, your n equal to 2 over 3. When tau equal to minus 1, your n equal to 1. Okay, tau equal to 0. So your n equal to 4 over 3. And then tau equal to 1. N equal to 5 over 3. And then when tau equal to 3, your n equal to 2. Okay, so let's draw the new axis underneath. Okay, now the n being replaced by tau. So now let's draw the n new axis. When minus 3, it is 1 over 3. When it is 2, so it is 2 over 3. When it is 1, it is 1. Minus 1 is 1. 0 is 4 over 3. 1, 5 over 3. 2, 2. of missing the 2. When tau equal to 2, when tau equal to 2, it is 2. When 2, it is 2. And then day 3, tau equal to positive 3. So the n equal to 7/3. Okay, 7/3. So obviously, when you have a point, you don't have to consider the signal. So you can just ignore this point, this point, this point, this point can be removed, and this one as well. So what's remain is just the whole number, the amplitude at the whole number. So you have the signal at 1, okay, originally at -1, now it's 1, the amplitude is there, the amplitude is -1. And next one you have at 2, okay, this one is 0, 1, 2, okay, this one, the amplitude is 4. So that's the only signal you have. Then you need to draw it nicely. So you don't have negative value, so it's 0, 1, 2, 3, and so on. This is your n. So you have 1, the signal is -1, and then you have at 2, you have the amplitude of 4. Okay, let's compare. So there you are, you have the final signal. Okay, so that's it for discrete time signal operation.